Welcome friends. In the previous session we have stated and given two proofs for the Sylows theorem. In this session we start with the third proof of Sylows theorem. We will also state and prove second and third parts of Sylows theorem giving some of its applications. Before going into the details of the third proof, we briefly outline the different steps in the proof. Step 1. We will first show that the symmetric groups S p raised to r P a prime all have P Sylows subgroups. Step 2. We will show that if a group G is contained in the group M and M has a P Sylows subgroup, then G also has a P Sylows subgroup. Step 3. We will show via Cayley's theorem that we can use S p raised to k for large K as our M. With this, theorem will be proved. In carrying out this program in detail, we will have to know how large a P Sylows subgroup of S p raised to r should be. For this, one should know what power of P divides P raised to r factorial. To carry out another vital step in this rough sketch, it will be necessary to introduce a new equivalence relation in groups and the corresponding equivalence classes known as double cosets. This will have several payoffs, not only in pushing through the proof of Sylows theorem, but also in getting us the second and third parts of the full Sylows theorem. Now we will find what power of P of a prime exactly divides P raised to k factorial. Definition 1. For k is equal to 1 2 etc. n of k is defined as the positive integer m such that P raised to m divides P raised to k factorial, but P raised to m plus 1 does not divide P raised to k factorial. Lemma 1. N of k is equal to 1 plus P plus etc. plus P raised to k minus 1. Proof. If k is equal to 1, then since P factorial is equal to 1 into 2 into etc. into P minus 1 into P, it is clear that P divides P factorial, but P square does not divide P factorial. Hence, n of 1 is equal to 1 as it should be. What terms in the expansion of P raised to k factorial can contribute to powers of P dividing P raised to k factorial? Clearly, only the multiples of P, that is P, 2P etc. P raised to k minus 1 into P. In other words, n of k must be the power of P which divides P into 2P into 3P into etc. into P raised to k minus 1 into P, that is equal to P raised to k minus 1 into P raised to k minus 1 factorial. But then n of k is equal to P raised to k minus 1 plus n of k minus 1. Similarly, n of k minus 1 is equal to P raised to k minus 2 plus n of k minus 2 and so on. Write these out as n of k minus 1 is equal to P raised to k minus 1, n of k minus 1 minus n of k minus 2 is equal to P raised to k minus 2 etc. n of 2 minus n of 1 is equal to P, n of 1 is equal to 1. Adding these up with the cross cancellation, we obtain n of k is equal to 1 plus P plus etc. plus P raised to k minus 1 as desired. Now we show that S p raised to k has a P Sylows subgroup, that is, we shall show, in fact produce, a subgroup of order P raised to n of k in S p raised to k. Lemma 2. S p raised to k has a P Sylows subgroup, that is, S p raised to k has a subgroup of order P raised to n of k. Proof. We go by induction on k. If k is equal to 1, then the element cycle 1 2 etc. P in SP is of order P and generates a subgroup of order P. Since n of 1 is equal to 1, the result certainly checks for k is equal to 1. Suppose the result is true for k minus 1. We want to show that it then must follow for k. Divide the integers 1 2 etc. P raised to k into P sets, each with P raised to k minus 1 elements as follows. Set consisting of 1 2 etc. P raised to k minus 1, set consisting of P raised to k minus 1 plus 1, P raised to k minus 1 plus 2 etc. 2 into P raised to k minus 1 etc. set consisting of P minus 1 into P raised to k minus 1 plus 1 etc. P raised to k. The permutation sigma defined by sigma is equal to the product of the cycles, cycle 1 P raised to k minus 1 plus 1, 2 P raised to k minus 1 plus 1 etc. P minus 1 times P raised to k minus 1 plus 1 etc. cycle j P raised to k minus 1 plus j 2 times p raised to k minus 1 plus j etc. p minus 1 times p raised to k minus 1 plus j etc. the cycle p raised to k minus 1 2 times p raised to k minus 1 etc. p minus 1 times p raised to k minus 1 p raised to k has the following properties. 1. Sigma raised to p is equal to E. 2. If tau is a permutation that leaves all I fixed for I greater than p raised to k minus 1, hence affects only 1, 2 etc. p raised to k minus 1, then sigma tau sigma inverse moves only elements in the set p raised to k minus 1 plus 1, p raised to k minus 1 plus 2 etc. 2 into p raised to k minus 1, and more generally sigma raised to j tau sigma raised to minus j moves only elements in the set j times p raised to k minus 1 plus 1, j times p raised to k minus 1 plus 2 etc. j plus 1 times p raised to k minus 1. Consider A is equal to collection of all tau belongs to sp raised to k such that tau of I is equal to I if I greater than p raised to k minus 1. A is a subgroup of s p raised to k and elements in A can carry out any permutation on 1, 2 etc. p raised to k minus 1. From this it follows easily that A is isomorphic to s p raised to k minus 1. By induction, s p raised to k minus 1 has a subgroup, say p naught of order p raised to n of k minus 1. Let T is equal to p naught into sigma p naught sigma inverse into sigma square p naught sigma raised to minus 2 etc. sigma raised to p minus 1 p naught sigma raised to minus p minus 1, that is equal to p naught into p 1 into etc. p minus 1, where p I is equal to sigma raised to I p naught sigma raised to minus I. Each p I is isomorphic to p naught and has order p raised to n of k minus 1. Also, elements in distinct p i's influence non-overlapping sets of integers, hence commute. Thus, T is a subgroup of s p raised to k. Since p I intersection p j is equal to the trivial group, if 0 less than or equal to I not equal to j less than or equal to p minus 1, we see that order of T is equal to order of p naught raised to p, that is equal to p raised to p times n of k minus 1. Still, T is not the p Sylows subgroup we seek. Since sigma raised to p is equal to E and sigma raised to I into p naught into sigma raised to minus I is equal to p I, we have sigma t sigma inverse is equal to T. Let P is equal to the set of all sigma raised to j times T such that T belongs to T, where 0 less than or equal to j less than or equal to p minus 1. Since sigma does not belong to T and sigma tau sigma inverse is equal to T, we have two things. Firstly, P is a subgroup of s p raised to k, and furthermore order of P is equal to P times order of T, that is equal to P times P raised to n of k minus 1 times P, that is equal to P raised to n of k minus 1 times P plus 1. We call it equation 1. We claim that P is the required p Sylows subgroup of s p raised to k. As n of k minus 1 is equal to 1 plus p plus etc. plus p raised to k minus 2, we have p times n of k minus 1 plus 1 is equal to 1 plus p plus etc. plus p raised to k minus 1 is equal to n of k. Hence, from equation 1 we have order of p is equal to p raised to n of k, and hence p is a p Sylows subgroup of s p raised to k. Let us remark about the proof. Not only does it prove the lemma, it actually allows us to construct the p Sylows subgroup inductively. We follow the procedure of the proof to construct a 2 Sylows subgroup in S2 square is equal to S4. Example 1. Construct a 2 Sylows subgroup in S2 square is equal to S4. Solution. Divide 1, 2, 3, 4 into set 1, 2 and set 3, 4. Let P naught is equal to cyclic group generated by the cycle 1, 2 and sigma be the product of the cycles cycle 1, 3 and cycle 2, 4. Then P1 is equal to sigma P naught sigma inverse is equal to the cyclic group generated by the cycle 3, 4. Our 2 Sylows subgroup is then the group generated by the product of the cycles cycle 1, 3 and cycle 2, 4, and T is equal to P naught into P1, that is equal to the set consisting of cycle 1, 2, cycle 3, 4, product of the cycles 1, 2 and 3, 4 and the identity permutation. In order to carry out the program of the third proof, that we outlined, we now introduce a new equivalence relation in groups. Definition 2. Let G be a group, A and B be subgroups of G. If x and y belongs to G, define x related to y if y is equal to AXB for some A belongs to A and B belongs to B. It can be easily proved that the relation defined above is an equivalence relation on G. The equivalence class of x belongs to G is the set AXB is equal to the set of all AXB such that A belongs to A and B belongs to B. Definition 3. The set AXB is equal to the set of all AXB such that A belongs to A and B belongs to B, seen just above, is a double coset of A and B in G. If A and B are finite subgroups of G, the double coset AXB need not be a subgroup of G. Yet we ask how many elements are there in the double coset AXB. The answer is given in the following lemma. Lemma 3. If A and B are finite groups of G, then order of AXB is equal to order of A times order of B by order of A intersection XBX inverse. Proof. Consider the mapping T from AXB to AXBX inverse defined by T of AXB is equal to AXBX inverse. Clearly T is 1 to 1 and onto. Thus order of AXB is equal to order of AXBX inverse is equal to order of A times order of XBX inverse by order of A intersection XBX inverse, since XBX inverse is a subgroup of G of order of B. That is equal to order of A times order of B by order of A intersection XBX inverse. Lemma 4. Let G be a finite group and suppose that G is a subgroup of the finite group M. Suppose further that M has a p Sylows subgroup Q, then G has a p Sylows subgroup P. In fact, P is equal to G intersection XQ X inverse for some x belongs to M. Proof. Before presenting the details of the proof, we translate the hypothesis somewhat. Suppose that p raised to m divides order of m, but p raised to m plus 1 does not divide order of m, and Q is a subgroup of m of order p raised to m. Let order of G is equal to p raised to n times t, where p does not divide t. We want to produce a subgroup P in G of order p raised to n. Consider the double coset decomposition M given by G and Q. M is equal to union GXQ, where X corresponds to one element from each double coset. Then order of GXQ is equal to order of G times order of Q by order of G intersection XQ X inverse, that is equal to p raised to n times t times p raised to m by order of G intersection XQ X inverse. Since G intersection XQ X inverse is a subgroup of XQ X inverse, its order is p raised to m suffix x. Claim. M suffix x is equal to n for some x belongs to m. To prove the claim, we note that order of GXQ is equal to p raised to n times t times p raised to m by p raised to m suffix x, that is equal to t times p raised to m plus n minus m suffix x. We call it equation 2. If the statement of the claim is not true, then n minus m suffix x greater than or equal to 1. So from equation 2 it follows that order of GXQ is divisible by p raised to m plus 1. Now since m is equal to union of GXQ and this is a disjoint union, order of m is equal to summation GXQ, the sum running over one element from each double coset. But p raised to m plus 1 divides order of GXQ, hence p raised to m plus 1 divides order of m. This contradicts the fact that p raised to m plus 1 does not divide order of m. Thus m suffix x is equal to n for some x belongs to m, hence the claim is proved. Now m suffix x is equal to n for some x belongs to m implies order of G intersection XQ X inverse is equal to p raised to n. Since G intersection XQ X inverse is equal to p is a subgroup of G and has order p raised to n, the lemma is proved. Third proof of Sylows theorem. By Cayley's theorem, we can isomorphically embed our finite group G in Sn, the symmetric group of degree n. Pick k so that n less than p raised to k. Then we can isomorphically embed Sn in Sp raised to k by acting on 1 to etc. n only in the set 1 to etc. n etc. p raised to k. Hence G is isomorphically embedded in Sp raised to k. By lemma 2, S p raised to k has a p Sylows subgroup. Hence, by lemma 4, G must have a p Sylows subgroup. This completes the third proof of Sylows theorem. Second and third parts of Sylows theorem and applications of Sylows theorems. Theorem 1. Second part of Sylows theorem. If G is a finite group P A prime and P raised to n divides order of G, but P raised to n plus 1 does not divide order of G, then any two subgroups of G of order P raised to n are conjugate. Proof. Let A and B be subgroups of G, each of order P raised to n. Claim. A is equal to GB G inverse for some G belongs to G. Decompose G into double cosets of A and B. G is equal to union of AX B. By lemma 3, order of AX B is equal to order of A times order of B by order of A intersection X B X inverse. If A is not equal to X B X inverse for every X belongs to G, then order of A intersection X B X inverse is equal to P raised to M, where M less than n. Thus, order of AX B is equal to order of A times order of B by P raised to M, that is equal to P raised to n times P raised to n by P raised to M, that is equal to P raised to 2n minus M, and 2n minus M greater than or equal to n plus 1. Since P raised to n plus 1 divides order of AX B for every x, and since order of G is equal to summation order of AX B, we would get the contradiction P raised to n plus 1 divides order of G. Thus, A is equal to GB G inverse for some G belongs to G. This completes the proof. Third part of Sylows theorem gives information on the number of p Sylows subgroups. Knowing that for a given prime P, all p Sylows subgroups of G are conjugate allows us to count up precisely how many such p Sylows subgroups are there in G. Before stating the third part of Sylows theorem, we consider the following lemma. Lemma 5. The number of p Sylows subgroups in G is equal to order of G by order of normalizer of P, where P is any p Sylows subgroup of G. In particular, the number is a divisor of order of G. Proof. Let P be a p Sylows subgroup of G. The normalizer of P is given by normalizer of P is equal to the set of all x belongs to G, such that xp x inverse is equal to P. We first show that the number of distinct conjugates xp x inverse of P in G is the index of normalizer of P in G. Our method of proof is to show that two elements in the same right coset of normalizer of P in G yield the same conjugate of P, whereas two elements in different right cosets of normalizer of P in G give rise to different conjugates of P. In this way, we shall have a one-to-one correspondence between conjugates of P and right cosets of normalizer of P. Suppose that x and y belongs to G are in the same right coset of normalizer of P in G. Thus, y is equal to nx, where n belongs to normalizer of P and np n inverse is equal to P. Therefore, since y inverse is equal to nx all inverse is equal to x inverse n inverse and n inverse Pn is equal to P, we have y inverse Py is equal to x inverse n inverse Pnx, that is equal to x inverse n inverse npx, that is equal to x inverse Px, and hence x and y result in the same conjugate of P. If on the other hand x and y are in different right cosets of normalizer of P in G, we claim that x inverse Px not equal to y inverse Py. If this is not the case, from x inverse Px is equal to y inverse Py, we obtain yx inverse P is equal to Pyx inverse, which implies that yx inverse belongs to normalizer of P. However, this declares that x and y to be in the same right coset of normalizer of P in G, contradicting the fact that they are in different cosets. Thus, the number of distinct conjugates xpx inverse of P in G is the index of normalizer of P in G. Since p Sylows subgroups of G are conjugates to P, we have number of p Sylows subgroups in G equals to order of G by order of normalizer of P. In particular, the number is a divisor of order of G. This completes the proof. The next theorem, third part of Sylows theorem, says about the number of p Sylows subgroups there are for a given prime P in G. We go into this now. The technique will involve double cosets again. Theorem 2, third part of Sylows theorem. The number of p Sylows subgroups in G for a given prime is of the form 1 plus k times P. Let P be a p Sylows subgroup of G. We decompose G into double cosets of P and P. Thus, G is equal to union of Pxp. We now find the number of elements in Pxp. By lemma 3, we know that order of Pxp is equal to order of P square by order of P intersection Xp x inverse. Thus, if P intersection Xp x inverse not equal to P, then P raised to n plus 1 divides order of Pxp, where P raised to n is equal to order of P. This is equivalent to saying that if x does not belong to normalizer of P, then P raised to n plus 1 divides order of Pxp. Also, if x belongs to normalizer of P, then Pxp is equal to P into Px, that is equal to P square x is equal to Px. So, order of Pxp is equal to P raised to n in this case. Now, order of G is equal to summation taken over x belongs to normalizer of P of order of Pxp plus summation taken over x does not belong to normalizer of P of order of Pxp, where each sum runs over one element from each double coset. However, if x belongs to normalizer of P, since Pxp is equal to Px, the first sum is merely summation taken over all x belongs to normalizer of P of order of Pxp over the distinct cosets of P in normalizer of P. Thus, this first sum is just order of normalizer of P. As P raised to n plus 1 divides order of Pxp when x does not belong to normalizer of P, we have P raised to n plus 1 divides summation taken over all x does not belong to normalizer of P of order of Pxp. Hence, we can write summation taken over all x does not belong to normalizer of P of order of Pxp is equal to P raised to n plus 1 times u. Therefore, order of G is equal to order of normalizer of P plus P raised to n plus 1 times u. So, order of G by order of normalizer of P is equal to 1 plus P raised to n plus 1 times u by order of normalizer of P. Now, order of normalizer of P divides order of G, since normalizer of P is a subgroup of G. Hence, P raised to n plus 1 times u by order of normalizer of P is an integer. Also, since P raised to n plus 1 does not divide order of G, P raised to n plus 1 cannot divide order of normalizer of P. But then P raised to n plus 1 times u by order of normalizer of P must be divisible by P. So, we can write P raised to n plus 1 times u by order of normalizer of P is equal to k times P, where k is an integer. Putting all this information into equation 4, we obtain order of G by order of normalizer of P is equal to 1 plus Kp. By lemma 5, order of G by order of normalizer of P is the number of P Sylows subgroups in G. Hence, we have the number of P Sylows subgroups in G for a given prime is of the form 1 plus Kp. Applications of Sylows theorem. We recall that a group is simple if it has no proper non-trivial normal subgroups. Example 2. Let G be a group of order 11 square times 13 square. Determine how many 11 Sylows subgroups and how many 13 Sylows subgroups are there in G. Also show that any group of order 11 square into 13 square is abelian. Solution. The number of 11 Sylows subgroups by third part of Sylows theorem is of the form 1 plus 11k. Also by lemma 5, this must divide 11 square times 13 square. As 1 plus 11k is relatively prime to 11, this implies 1 plus 11k divides 13 square. The only factor of 13 square of the form 1 plus 11k is 1. So, there must be only one 11 Sylows subgroup in G. By second part of Sylows theorem, all 11 Sylows subgroups are conjugate, and hence we conclude that the 11 Sylows subgroup is normal in G. The number of 13 Sylows subgroups are of the form 1 plus 13k and must divide 11 square times 13 square, hence must divide 11 square. The only factor of 11 square of the form 1 plus 13k is 1. So, there must be only one 13 Sylows subgroup in G. By second part of Sylows theorem, all 13 Sylows subgroups are conjugate, and hence we conclude that the 13 Sylows subgroup is normal in G. We now know that G has a normal subgroup A of order 11 square and a normal subgroup B of order 13 square. We know that any group of order P square is abelian, hence A and B are both abelian. Since A intersection B is equal to the trivial group E, we have order of AB is equal to order of A times order of B by order of A intersection B, that is equal to order of A times order of B, that is equal to 11 square times 13 square, that is equal to order of G. Thus, AB is a subgroup of G having order of G. So, AB is equal to G. Finally, if A belongs to G and B belongs to G, then AB A inverse B inverse is equal to A into B A inverse B inverse belongs to A, since A is normal, and AB A inverse B inverse is equal to AB A inverse into B inverse belongs to B, since B is normal. Thus, AB A inverse B inverse belongs to A intersection B, the trivial group. This gives AB A inverse B inverse is equal to E, and so AB is equal to BA for A belongs to A and B belongs to B. This together with AB is equal to G, A and B are abelian, allows us to conclude that G is abelian. Hence, any group of order 11 square times 13 square must be abelian. Example 3. Let G be a group of order 72, that is, order of G is equal to 2 cube into 3 square. How many 3 Sylows subgroups can there be in G? According to third part of Sylows theorem, this number is 1 plus 3k. Then by lemma 5, 1 plus 3k divides 72, and since 1 plus 3k is prime to 3, we must have 1 plus 3k divides 8. The only factors of 8 of the form 1 plus 3k are 1 and 4. Hence, 1 plus 3k is equal to 1 or 1 plus 3k is equal to 4 are the only possibilities. In other words, G has either one 3 Sylows subgroup or 4 number of 3 Sylows subgroups. If G has only one 3 Sylows subgroup, since all 3 Sylows subgroups are conjugate, this 3 Sylows subgroup must be normal in G. In this case, G would certainly contain a non-trivial normal subgroup. On the other hand, suppose the number of 3 Sylows subgroups of G is 4. According to lemma 5, if P is a P Sylows subgroup of G and if N is the normalizer of P, then index of normalizer N in G is equal to the number of P Sylows subgroups of G. Hence, if the number of 3 Sylows subgroups is 4, then the index of the normalizer N of a 3 Sylows subgroup in G is 4. 72 does not divide 4 factorial is equal to index of N factorial. Now, using the result, if G is a finite group and H not equal to G is a subgroup of G such that order of G does not divide index of H factorial, then H must contain a non-trivial normal subgroup of G, N must contain a non-trivial normal subgroup of G of order at least 3. Thus, here again we can conclude that G contains a non-trivial normal subgroup. We summarize that any group of order 72 must have a non-trivial normal subgroup, hence cannot be simple. Now, let us conclude this session. In this session, we have considered second and third parts of Sylows theorem. Some of the applications of the theorem have been discussed. Before we attend the next unit, please try to answer the following questions. Use the method for constructing the P Sylows subgroup of S P raised to k to find generators for a 2 Sylows subgroup in S8. If P is a prime number, give explicit generators for a P Sylows subgroup of S P square. Discuss the number and nature of the 3 Sylows subgroups and 5 Sylows subgroups of a group of order 3 square times 5 square.
References. Topics in Algebra, Ian Hairston, Wiley Eastern Limited, New Delhi 1975. Basic Algebra Volume 1, Nathan Jacobson, Hindustan Publishing Corporation, India, Delhi 1993. A first course in Abstract Algebra, John B. Fraley, 5th edition, Addison Wesley, California 1999. A course in Abstract Algebra, Vijay K. Khanna, S. K. Bambri, Vigas Publishing House Private Limited, New Delhi 1996. University Algebra, N. S. Gopalakrishnan, Wiley Eastern Limited, New Age International Limited, New Delhi 1995.